Hello, so in this video, what we are going to do is we're going to solve some problems on combined footing. This is part of Unit 3, Shallow Foundation, wherein you'll be asked to determine sizes of combined footing. The combined footing always doesn't have to be of this shape, okay? Combined footing, by definition, it means when a single footing is provided for two columns, okay? Now, this shape of this kind of combined footing can be trapezoidal as shown in the figure, or it can even be rectangular. Now this is a typical example which has been appearing in your question papers, and we'll try to understand how do we sort out how do we get the size of the footing. The problem statement reads that trapezoidal footing is to be provided for two square columns of 35 and 40 centimeter size. Okay, so sizes of the columns are unequal. One is 35, one is 40. 6 meter apart. Okay. Bearing capacity of the soil is 400 kilonewton per square meter. Bigger column carries 5000 kilonewton and smaller one carries 3000 kilonewton. Design a suitable size of the footing. The size word is in capital because you are just doing proportioning. No RCC part of the design is actually carried out over here. So what you are told is to design a suitable size of the footing such that it does not extend beyond the columns. Now why is this statement extend beyond the columns is given to you? Because usually when you have two footings, I'll just draw here, and you have two footings like this, okay, it always has some cantilever around. This cantilever will be there. Now, even if it is trapezoidal, usually you will have columns somewhere here. Okay, usually these cantilevers are also more or less equal. That's how we start with the dimensioning of the footings. Okay, but over here, the problem says that it should not have any cantilever. Why? Because it said that it does not extend beyond columns. So cantilever cannot be on all the three sides. On two sides it's allowed. For maybe multiple reasons, we don't want to know. But maybe there is a site restriction on having cantilevers. So you have to design the size of the footing in such a way that it does not extend beyond the columns. Now, when such problems will be given, the figure will not be given. You will have to construct a figure. The most obvious thing is when you have a bigger column, the bigger column should have the bigger size of the trapezoidal footing. Okay? It's given that the columns are 6 meters apart. So now this 6 meter is the clear span between columns. I have named Q1 and Q2 as the loads that are coming from the column. So Q1 will be the bigger load, that is equal to 5000, and Q2 will be 3000. Why? Because Q2 is a smaller column, so obviously it will carry the lesser load, and it should be adjacent to the smaller side of the trapezoidal footing. Okay, all these things you should know before you start solving the problem. Okay, now 6 meter is given. So what will be the center to center distance between the two columns? So 6, it's a 40 and 35 centimeter size. So total size of the columns is 40 plus 35 is 75. So 6 plus half of 75 will be your center to center. And total length of the trapezoidal footing, as there is no cantilever told, it will be equal to the one dimension will be equal to the face to face, that is outer end distance between the outer faces of the columns. That will be 6.75. I hope all these things are clear. Now I have just marked a point here. So this is basically the resultant of these two downward forces. It is resultant of the loads that are coming on the column. So it will be somewhere in between the two columns, a little bit closer to this column, right? Because this is a heavier one, so resultant will be somewhere a bit closer to this column. So what I'll do, I will mark the distance between Q1 and the resultant as x. Okay, I'll mark it as x. And the distance between this point where resultant is acting and the outer edge of the trapezoidal footing as, this I'll mark as x bar. Alright, so let's start solving the problem. The first thing, let's assume that A and B are the sides of footing. So this will be my B. Okay, this will be my B, and this will be my A side of the foot. So I'll mark it as B on this side. Okay, now Q1 is equal to 5000 and Q2 is equal to 3000 kilonewton, right? So area of the footing, that's a trapezoidal footing. What is the formula for the area of the footing? It will be A plus B into the distance between A plus B, the perpendicular distance, that is L, the whole by 2. So that is equal to A plus B, whole thing is 6.75 by 2. That's the area. Let's say QA is the allowable bearing capacity. So allowable bearing capacity, so QA allowable, what is the formula for QA allowable? It is the total load upon area. Now how I am writing it is as area is equal to total load upon QA. Just rewriting this equation. So that gives me Q1 plus Q2, that is the total load, divided by QA will be equal to what we determined earlier, A plus B into 6.75 upon 2. Now I substitute over here 5000 plus 3000 divided by, what is QA? 400 is equal to A plus B into 6.75 by 2. This gives me an equation A plus B is equal to 5.92 meters. Now we had studied this in the theory. First thing is, wherever the centroid of the area, okay, area meaning wherever the centroid of this shape, trapezoidal shape, that should intersect with the centroid of the forces, applied forces. So this point where I have shown Q1, Q2, where the resultant is acting, this only should be the centroid of the area. That's why I have marked the distance between this point and A as x bar. Okay. So now what is the equation for x bar which we have learned in our first year? Right? What is the equation for the centroid of a trapezium? A plus 2b upon A plus b into L by 2. Sorry, L by 3. So now over here I'll just write, let x be the distance between resultant, what is the resultant? Q1 plus Q2 okay, and center of Q1. Q1 I'm just saying, right, column 1, or you can write here as column 1. Now if that is the case, then what will be the value of x bar minus x? Look at the figure and tell me what will be the value of x bar minus x. It will be half of the dimension of column 1, so that will be 0.2 meters. So the next thing we are going to do is take moments about this point. Which point? The centroid. So I'm taking moments about centroid. Okay. Now what I will do? I will equate the clockwise moment to anti-clockwise moment. So what I will get? Q1 into, what is the distance between Q1 and this point? X. Okay. So this is going to cause anti-clockwise moment, correct? Similarly, this will be equal to, anti-clockwise moments are equated to clockwise moments. So this will be Q2 into, what is the distance between Q2 and X? It will be 6.375, correct, minus X, correct? So this full thing is 6.375 center to center, minus X will be the distance between Q2 and this point. So this will give me X is equal to, calculate, X is equal to, you will pause the video and calculate, you will get the answer as somewhere around 2.4 meters. So now X is equal to 2.4, that means what will be the value of X bar here? If X is 2.4, what will be the value of X bar? X bar will be 2.6 meters. Now you have equation for X bar, so you substitute it back in this equation. Okay, equation for X bar, 2.6 is equal to A plus 2B upon A plus B into L by 2. So now L is the full distance of the footing, so that is 6.75 by 3. So now what do you have? You have this one equation in terms of A and B, and you have another equation here in terms of A and B. So you substitute this A plus B is equal to 5.92 here in the denominator. What you will get total, you solve this, okay, substitute A plus B is equal to 5.92. So you will get A plus 2B in this equation as, I think, 1.38. You have another equation A plus B as 5.92. Solve this simultaneously. You will get answer A is equal to somewhere around 4.99. So I'll approximate this to 5 meters. And B is equal to, I will get this as 0.92. I'll approximate this as 0.95 meters. Okay, so that is my dimension. Now this is another problem. This is again on combined footing. Okay, I have kept the column size same and the distance also same. What I am going to tell you is how is the process different from the previous problem that we solved. Okay, over here I have slightly altered the bearing capacity so that I get some legible answers. Okay, then bigger column is 900 kilonewtons and smaller is 600 kilonewtons. Now what they've asked you to design a footing such that the projection, this is more important, the projection beyond the bigger column does not exceed 0.6 meters. Now which is a bigger column? 45 centimeter is a bigger column. The projection beyond 45 centimeters, so the cantilever, here they are allowing you to keep a cantilever, but they are limiting its size. So you cannot have more than 0.6 meters. So how will the figure look like? Now this is a rectangular footing. Again, the diagram will not be given to you in your problem statement. You have to construct the figure based on the problem statement. Now this is a rectangular footing, correct? and you are allowed to keep the cantilevers for both the columns. So I've just drawn a typical figure. Now over here what you are required to do is you're required to mark all these values. What will be the out to out dimension, what will be the center to center dimension, in to in dimension is given to you, right? This is a smaller column and this is bigger column. Okay, what else is given to you is you are also told that the cantilever should not go more than 0.6 meters. This is told to you. So now here I will start the problem saying that let the area be L into B, as we started with small a into b for the previous case. So this will be my L and this becomes my B. It's fairly simple because this is a rectangle. So now taking the moments about centroid. So what I'm doing, I'm just taking moments about centroid. Where is my centroid? Here at this point. Okay, maybe I'll use some other color. Okay, this is my centroid. Virtual. I don't know where exactly it is, but I've just decided I'll take the moments about centroid. So what do I get? I get 900 into, so where is my 900? This is my 900 kilometer. Okay, into this I will mark as distance between this 900 and this pink point. I'll mark it as x bar. Okay, 900 into x bar will be equal to 700 into 6.4 minus x bar. So my x bar, which is the distance of the centroid from the center of column Q1, is 2.8 meters. Right? Now, for removal of eccentricity, this x bar plus 0.6, okay, this x bar plus 0.6 should be equal to, so see, pink point is the centroid of the first system, 600 and 900 and 700 kilonewton. Now the same has to be the centroid of the footing. So this point, this x bar 2.8 has to be half of L by 2. So 2.8 plus 0.6, okay, so this 2.8 plus 0.6 plus half of this is also there, plus 0.45 by 2 has to be equal to L by 2. So this will give me L is equal to, you all please calculate. So the moment you know the L value, how do you get the value of B? Okay, B will be given as total load Q1 plus Q2 divided by bearing capacity. See, it's actually the equation is Q1 plus Q2 upon area, that is L by B, is equal to your bearing capacity allowable. So I'm just rewriting it ulta. So B is equal to QA into L. So this is known, this is known, this is known, this is known. This will give you the value of B. So this is your way to carry out the proportioning of rectangular footing. Very simple. So all you have to do is you find the centroid of the force system and say that that is the centroid of the area. So this you get from the Varignon's principle or simple principle of moment, and this you get from the geometry, the dimensions of centroid. You know the centroid of the rectangle is going to be at half of the length. So that half of the length should be equal to whatever you have got from the distance, from the value of x bar from the moments principle. Now if you are getting confused what is this x bar, you just take it as x only. X bar usually represents the x dimension of the centroid. So let's not get confused. So this is my x from the centroid of the column. So you get the value of x, you get this plus this has to be half, so that the physical centroid coincides with the centroid of force system. So then you create this. It's very simple. So that's how to solve a problem for combined.